All right, now let's talk some practical stuff that we can do. Talk about some practical stuff we can do. Let's go back to the budget constraint. Budget constraint's going to be our buddy. We're going to get as much mileage as we can out of the budget constraint. So my budget constraint is the sum of the xi pi equals m. Right? Everybody agrees with that? And now I'm going to look at what happens changing everything at the same time. I'm going to change x's, p's, and m's. Right? So I'm going to shift from one equilibrium to another, changing both prices and income, and letting people respond by changing their mix of consumption. So it's just a total change. So total derivative of this is the sum of xi dpi plus the sum of pi dxi equals dm. Okay? Everybody agrees with that, right? Yes, no, maybe so. Okay. Then I'm going to take that equation and I'm going to divide by the budget constraint. Just divide through. So then I'm going to get the sum of the xi dpi over the sum of the xi pi plus the sum of the pi dxi divided by the sum of xi pi equals dm over m. Okay? So this side, okay, is the percentage change in income, right? That's the percentage change in nominal income. And what I want to say, I'm going to call this dp. That's the change in prices. And I'm going to call this term here dx and equals percentage change. I'm going to make a delta. It's percentage change. Delta p plus delta x equals delta m. And I'm going to say this is the percentage change in prices, this is the percentage change in consumption, and this is the percentage change in income. And I want to call this price change, quantity change, and this is the income change. So I want to think about the budget constraint tells me that if I increase income by 10% and I increase prices in the aggregate by 3%, then real consumption could go up by 7%. That's really what this says, right? So it's a way of dividing it up. And I want to ask you a question, which is, which one do I want to think about? Why is that a reasonable way to think about the change in consumption or the change in quantities? Any idea why that's a sensible measure? Why we measure, why economists might say, that's a pretty good way to measure the change in consumption. Okay, yeah, but more fundamentally. Think about it. That is, I'm weighting the quantity changes by prices. Why does weighting the quantity changes by prices make sense? Why should I rate something that costs $10 twice as much as something that costs $5? Yeah.
Equilibrium, that's how much you value.
Exactly. This, in fact, can be thought of as a first-order approximation to the utility function, right? That's what we did in Lecture 1. In Lecture 1, we showed that the sum of pi dxi is a first-order approximation to the dollar value of the change in income. In consumption, right? It's a first-order approximation to the utility function. So And to first order, this is going to accurately measure whether his consumption in real terms is going up or going down. Right? We're going to be looking. How much does he value each good? How much did each good change? We're going to total up over all those goods. You got a +1 times $10, and a -1 times $5, and a +2 times $12. And you're just going to add them all up. And you can say, well, that one was worth 12 plus, this one was worth 17 minus, and I'm going to add them up. And I'm going to say, based on what I think his values of the different goods are, he's better off or he's worse off. It's a first order approximation to the utility function. Right? What about this term? Measuring how prices have changed. It says I'm going to weight each of the price changes by the quantity consumed. Why does that make sense? First off, you should realize if this one makes sense, that one's going to have to make sense. And if this one doesn't make sense, that one can't make sense. Everybody realizes that. You can't have an equation in which this makes sense and that doesn't, because this is what it is. Anytime you decompose something into two parts, first part makes sense, second part has to make sense. First part is wrong, second part, right? Everybody understands. They add up to the truth. If they add up to the truth and you underestimate one, what must be true? You overestimated the other one, and vice versa. You can't, if they add up, you can't be right on one and wrong on the other. Okay? All right. But independent of that, independent of proof by elimination, why do we think that makes sense? What in the world tells me to measure whether prices are up or down by weighting the price changes by the quantities? Well, what would be the perfect measure of whether prices have gone up or down? The ideal measure. What would measure price changes perfectly? Yeah.
The maximum utility consumers could achieve at
Yeah, but what function measures whether the cost of living goes up or down? How about the cost function? That might be a good idea, right? The cost function measures the cost of obtaining a given level of utility. So a perfect measure of the cost would be C of P1 up to Pn U bar, right? What would a first order approximation to the cost function be? How do you take a first order approximation to a function? Well, it's C of P1 naught up to Pn naught U bar plus, what's a first order approximation? You take the sum, I equals 1 to n, partial C, partial Pi, right, times dPi. Everybody agrees with that? And a first order approximation is just the function at the starting point plus the derivatives times the changes in the prices. Everybody agrees with that? What are these? What's partial C, partial Pi? That's xi. So this is sum from I equals 1 to n of xi dPi. So the reason this term makes sense is because it's a first order approximation to the cost function. Okay? So when we got a bunch of prices changing at the same time, we want to ask did prices go up or down. We're going to weight those price changes by the quantities consumed. Yes?
That equation then that you first decomposed is a first order approximation itself.
It is.
Yeah.
So but what I'm saying is I could have split this up numerous different ways, but I split it up, this split, to say this is quantities and this is prices, has a virtue in that this is a first order approximation to the utility function, and this is a first order approximation to the cost function. Okay? People People understand how that works? So let me show you how this works. This is like the theory of how we measure things. How do we actually do it in practice? So the way we're going to carry this out in practice is you think about discrete data. I got two time periods. I got x1 naught up to xn naught, p1 naught up to pn naught, m naught, x11 up to xn1, p11 up to pn1, m1. Right? So that's my data. I got period 0 or condition 0 where we consume this mix of goods at these prices and this income level. Period 1, we consume this mix of goods at these prices and this income level. Right? And I want to look at the change over time. And I can write M1 over M naught equals the sum over I of xi1 pi1 over sum over I xi naught pi naught. Right? That's by definition. That is this income is the sum of all the expenditures. This income is the sum of all those expenditures, so the ratio has got to be that. We often do something like this, right? This is the sum of xi naught pi1 over the sum of xi naught pi naught times the sum of xi1 pi1 over the sum of xi naught pi1. And you'll notice that works because I got the same thing here and here. I've just introduced that term in both places. Well, what is this? What is the sum of xi naught pi1 divided by the sum of xi naught pi naught? That's asking the question, how much would it cost in period 1 to buy what I bought in period 0 compared to how much it cost in period 0? Right? The classic, what we call the spares price index, right? It's a price index that takes my period 0 bundle and asks how much would it cost to buy it now? And we say if this number is bigger than that number, we say prices went up. I can't afford for the same dollars to buy what I bought yesterday. And if this went down, I would say I can more than afford to buy what I bought yesterday today. Okay? Any questions that people have? And you'll notice that this is the same concept we had over here, because I'm comparing the cost of the same bundle at different prices. Right, if you want to write it in terms of changes, just subtract 1, and then you'll see it's xi naught pi1 minus pi0 divided by that. Right? It's like the change from 1. Right? So this is exactly what that formula is telling me to do. It's a first order approximation to the cost function. That's my Lasper's price index. This you see a little bit less, but it's important. This is what we call a quantity index. It's a quantity index because it's taking a fixed set of prices and valuing the two bundles at the same prices. Everybody understand that? Everybody understand why this is a quantity index? Because it's measuring what's different between the top and bottom is the quantities, and the prices we're using are, in this case, the period 1 prices. Sometimes people talk about base year. For this comparison, period 0 is the base year for my price index, and period 1 is the base year for my quantity index. Okay? If you want them to add up, it always got to work like that. You're going to use period 0 for your price index. You need to use period 1 for your quantity index. Okay? It's not unique to this problem. Every problem has that feature, right? Everybody understands that? Understand why that is? Just think about a map, right? I want to get from here to here, right? To get from here to here, I got two choices. If I can only move one direction at a time, right? I can go this way and then go that way. Or I can go this way and then go that way. Right? That's two choices. So I could have done this, could have done my price index with ones, and then I would have done my quantity index with zeros. That corresponds to these two paths. But I can't do this. I can't go this way and then go that way and end up here. It just doesn't work. Okay? That's why you got to do one at one and one at the other. If you want to get from A to B, you kind of got to move and then move. All right? Anyway, that's just kind of geometry of it. So this is the kind of way that we're going to approach prices and quantities. And why is this a decent way to go? I'm not saying it's a perfect way to go. What makes us motivated to think this makes sense is the fact that this is a first order approximation to which one? Which would be a first order approximation to what? Cost function, right? Because I got the same price, same quantities, and I'm comparing prices. This is a first order approximation to utility. Okay. So when people start talking about measuring quantities and prices using a price and quantity index approach, you might say, well, geez, why you do that? Isn't that some arbitrary way to like do things? Not really arbitrary. It's really got a lot of grounding in consumer theory. It tells us that, first order approximation. Okay. Any questions that people have? Here's my demand curve. And here's the price of good one. P1 naught, X1 naught. Here's X1, here's P1. So that's the price of good one. This is X1 of P1, P2 naught, up to Pn naught, M naught. Right? So that's my Marshallian demand curve corresponding to some initial set of prices, initial income, and I'm letting the price of good one vary. That traces out my Marshallian demand curve. That's my initial point. And if I'm just going to change the price of good one. All right. So when the price of good one goes down, how much of an increase in real income do I get? How much would my price index as my real income went up? Well, my price index actually corresponds to measuring my increase in real income by that area there. It says, well, good one got cheaper. And when good one got cheaper, how much income did I gain? Well, I got $1 cheaper and I'm buying 10 units, I gained 10 bucks. If I use the period one quantity to measure my gain, I'm going to tend to understate my gain from the fall in price, right? Why? Why does it tend to understate my gain? It says that's how much you'd gain if you couldn't substitute at all. It misses the substitution. What if I measured my gain not using my initial quantity, but I measured my gain using my new quantity? When the only thing changed was the price of good one. Well, then I would measure it by this big box. Then I would measure it by that big box. Right? Because I would be using the new quantity, 12 units times the change in price. The price went from $20 to $19. My consumption went from 10 units to 12 units. How much did I gain? Well, you gain more than 10 and gain less than 12. That's the answer. 12's too big, 10's too small. Right answer is somewhere between the two. All right? People understand how that works? And that's what we said. These are first order approximations. Right? This is a first order approximation. And I have two different first order approximations I could use. I could use my initial bundle, or I could use my new bundle. And it's not like one is better than the other. If I use the new bundle and the price of good one went down, I'm going to tend to overstate how much I gain from the price going down because I'm going to put more weight on it. On the other hand, if I use my original bundle, I'm going to tend to understate how much prices went down because I'm going to ignore the fact I can buy more. Similar way to think about it is if prices went up, that is going the reverse direction. When I use the big quantity, I'm going to overstate my loss because I'm going to ignore my ability to substitute away from it. So it really is always the same phenomenon. I'm always ignoring the ability to substitute. When prices go up, I ignore the fact that I can substitute away. When prices go down, I ignore the fact I can substitute toward. Right? That is that cost function. Remember, when we talked about the cost function, and we did that approximation for the stupid cost function, right? Stupid cost function was exactly that. It was the stupid cost function, right? It was how much you would gain or lose if you didn't change anything. So it's always going to overstate how much you lost, because it's going to say how much would you lose if you didn't make any adjustment. Right? Similarly, when we looked at the utility side, we did that quantity index. We approximated the indifference curve by the budget line. We said, well, that's okay locally, but that's going to tend to miss. If you're moving along the budget line, you're actually worse off. Because you're moving to something you could have picked before but didn't. Right? That's the problem. Both of these first order approximations are exactly that. But actually that's good, because they're first order approximations and we also know kind of which way they're off. We know they're pretty close, at least if things don't change too much. On the other hand, we also know they're either biased one way or the other, depending on which one we're looking at. So what I'm trying to tell you here is that consumer theory that we use to think about utility maximization and consumer choice is very helpful because it gives us a lot of empirical guidance as to how we can measure things. It says things like real GDP measured by weighting changes in quantities by the different prices that we see. Or a price index that looks at how things change for the cost of a given bundle. It's useful even if the bundle doesn't stay constant. Nothing here assumes that the bundle doesn't change. It's still a first order approximation even when the bundle doesn't change, and when the bundle does change. Okay.
All right, so we ended up talking about price and quantity indices last time, right? So I think where we had just started on it, we had said, look, I have sort of expenditure growth, xi t plus 1, pi t plus 1, divided by the sum of xit, pit. So we're going to look at the growth in expenditure over time. And again, this could be aggregate expenditure. This could be expenditure on a given category of goods. And we said, well, one way you could decompose that would be the sum of the xit pi t plus 1 divided by the sum of the xit pit. So that would be a period t-based price index because it's looking at the same bundle top and bottom. And we could then use also a quantity index. And the corresponding quantity index, PIT plus 1, divided by the sum of XIT, PIT plus 1. So you can see this works because I just inserted the same term here and here, so it cancels. And so you would call this like PT plus 1 over PT. And this could be thought of as QT plus 1 over QT, right? So that would be one way to decompose the growth in price and quantities into a price index here and a quantity index here. we said, well, what about this makes sense? Because, you know, I could have put my hat size here, right? And my hat size here, and this would also be a decomposition, right? Everybody realizes that, right? The fact that I put something here and put something here would decompose this, wouldn't make any sense, wouldn't be at all helpful in thinking about the world, but it would work. So you can't just say, well, it's a decomposition and therefore it makes sense. You got to say, well, why does it make sense? Well, the answer is, well, this is a good thing to look at because this is a first order approximation to the cost function, right? That is, this is essentially saying how much did the cost go up along the tangent line, right? When we talked about the cost function, we held the bundle fixed and that gave us the tangent line to the cost function. That's exactly what this is, right? This is just a tangent line. So we know that that tangent line is, people often say, well, it so I have this concave cost function and I'm looking along the tangent line. And you'll say, well, that overstates the increase in the cost of living. People often misinterpret that and say that it overstates the change in the cost of living. That's not true. It's biased in a particular direction, right? So when the cost of living is going down and I'm moving this way, it's actually understating the decline, right? The decline is bigger. It's always making it more like it look like it went up. So when the cost of living went up, I really am moving along this curve. My approximation is moving along this line. So I'm overstating the increase. When the cost of living is going down, I'm actually understating the decrease, right? Everybody understands? So it's not like it's always too big in absolute value. It's always too big in numeric value. It's always going that way. It's because the cost function is concave, I'm ignoring this guy's ability to adjust. I'm saying, look, even if he didn't make any changes to his consumption bundle, that's how much cost would rise. If he makes any changes, it's got to make cost of living, in the new case, be somewhat less than what I just laid out. Okay? Everybody understand that? All right, so that's this quantity, that's this price index, okay? All right, now this here is a quantity index. And that quantity index you can think of as basically approximating the guy's indifference curve by the budget line, right? That's what we're doing. We're approximating his indifference curve by the budget line. We're saying, look, I know one thing from theory, which is he's tangent to the budget line. And it doesn't matter if it's two dimensions, 3 dimensions, 1,000 dimensions. It doesn't matter. He's always going to have that place. He's going to be at that point where he's tangent. And because he's tangent, then changes in his utility can be approximated by how you would move along the budget line, right? So that is approximating the first order approximation to the utility function. Now you might say, well, geez, if it's a first order approximation to utility, what units is it in? It's in dollar units, right? It's the income equivalent required to give you that change in margin utility. I mean, that change in utility, right? We've kind of, if you go through the formula, there's a 1 over lambda term that's actually causing that to be in dollars, okay? Any questions that people have? All right? Any questions before we go forward? Now, there's nothing magical about this particular decomposition. We equally well could have decomposed it the reverse way. We could have made this sum of x I t plus 1 pi t plus 1 divided by x I t plus 1 pi t. So that would have been decomposing it using a price index based in t plus 1. But if I did that, then what I would need in order to make it add up again would be this same term here. So I would have ended up with a quantity index that's based in period t. Okay? So here, price index based in T, quantity index based in T plus 1. Here, this is T plus 1 base, and here it's T. And there's none of them, one of these, it's not like one of these is good and one of them is bad. They're just different, right? They're two alternatives. They're both approximations. In this picture, it sort of corresponds. If I go from here to here, I could approximate either along this line or I could approximate on that line. That is, I could take where I ended up and approximate along that line, or I could take where I started and approximate along that line. All right, and because it's concave, you can kind of see that in this example, if you're holding cost constant, I'm going to be somewhere between those two. One's too big, one's too small. That's the usual way of looking at it. In terms of the discussion people have of price indices, if this is really the starting year and the ending year, we usually call this a L'Esper's price index, and this is often called the Posh price index. They're just two corresponding differences. In a comparative statics exercise where you go from point A to point B or B to A, doesn't know which way you're going, you know, it just matters, am I using one point or the other? That's really it.